Dear students, I am Dr. R. S. Ramkumar, Head and Assistant Professor, Department of Mathematics at Sri Saranam College, Satur. Today we are going to see about the topics vertex cut and edge cuts, and also connectivity and edge connectivity of a given graph G in a graph theory, in a subject graph theory. The first definition is vertex cut and edge cut. So a subset V dash of the vertex set V of G of a connected graph G is a vertex cut of G if G minus V dash is disconnected. So first you consider a connected graph G. So there must exist a vertex set V of G. So from that vertex set, consider a subset V dash, and by removing the V dash from a graph G, then the resulting graph is disconnected. Then the vertex set V dash is a vertex cut of G. So by removing of certain vertices, the given graph should be disconnected. Then the subset V dash of a vertex set V of G is called a vertex cut. So it is K vertex cut if cardinality of V dash is equal to K. If there are K elements in V dash, then that set is called a K vertex cut. V dash is called a separating set of vertices of G. So it has one name, separating set of vertices of G. A single vertex V of a given graph G is a cut vertex of G. So it is totally different from vertex cut. So this one is a cut vertex. If that singleton V is a vertex cut of G, that means after removing the vertex V, a single vertex V, the graph must be disconnected. Then that V is said to be a cut vertex of G. So this one is a definition for vertex cut and a cut vertex. So consider the example. So in that figure, in that graph, if you remove V2, a single vertex V2, then the corresponding edges which is incident to V2 are also removed. Then V1 is separated from a given graph G, and V3, V4, V5, V6 are separated from V1. Now the graph is disconnected. Therefore the singleton V2 is a cut vertex. And also the set of all V3 and V4. So after removing V3 and V4, the vertices V1 and V2 are separated from V5 and V6. Now also the graph is also disconnected. Therefore the set of all V3 and V4 are also vertex cuts. Next one is the definition for edge cut. So G be a non-trivial connected graph with a vertex set V of G, and let capital S be a non-empty subset of V of G. So for S complement is equal to V minus S. Just removal of S from V, we get S complement or S bar. That should be non-empty. Let S comma S bar denote the set of all edges of G that have one end vertex in S and the other end vertex in S bar. A set of edges of G of the form S comma S bar is called the edge cut of G. And edge E is a cut edge of G if singleton E is a edge cut of G. An edge cut of cardinality K is called a K edge cut of G. So let us see the example for the edge cut. So here the edge subsets V3, V5 and V4, V5. So here V3, V4 belongs to the set S and their complement is V1, V2, V5, V6. So here the edges V3, V5, V4, V5 has the one end in the vertex in S, the other end in the vertex in S complement. These are all the edge cuts. So like that, V1, V2. Here V1 belongs to the set S, and V2 belongs to the complement of the set S. And V4, V6. So V4 belongs to the set S, and V6 belongs to the S complement. Here V1, V2, V4, V6 are the cut edges. So after removing the edges, we have a disconnected graph. So V1, V2, just removing the edge V1, V2, then the point V1 is separated from the given graph G. Like that, V4, V6, the removing of V4, the edge V4, V6, the vertex V6 is separated from the given graph G. So therefore the given graph is disconnected. So these are all the cut edges of a given graph G. So here we may take S is equal to V5 and S complement is equal to set of all V1, V2, V3, V4, V6 for the edge cut, the set of all V3, V5, V4, V5. I have already told you that for the edge cut V3, V5, V4, V5, S to be considered as a singleton V5 and S complement is considered as the V1, V2, V3, V4, V6. Next theorem. A vertex V of a connected graph G with at least 3 vertices is a cut vertex of G if and only if there exist vertices U and W of G distinct from V such that V is in every UW path in G. This one is a necessary and sufficient condition for a graph, a vertex to be a cut vertex of G. Proof. First you consider a cut vertex, let V be a cut vertex of a given graph G. So after removing the vertex V from G, then the graph is disconnected. That is, G minus V is disconnected. Now we have two components, at least two components named as G1 and G2. Just by taking U belongs to the vertex set of the first component G1 and W belongs to the vertex set of the second component G2. Then every UW path in G must contain V, or otherwise U and W would belongs to the same component of G minus V. Because of G minus V is disconnected graph, so there must exist V is in every UW path. So conversely, suppose that the condition of the theorem holds. That means if there exist the vertices U and W of G distinct from V such that V is in every UW path in G, we have to claim that V is a cut vertex of G. Then the deletion of V destroys every UW path in G. So after removing V from the given graph G, there must be a break between the vertex U and to the vertices U and W that destroys every UW path in G. Hence U and W lie in a distinct components of G minus V. Therefore G minus V is disconnected and hence V is a cut vertex of G. Next theorem is a necessary and sufficient condition for an edge to be a cut edge of a connected graph G. So an edge E is equal to xy is a cut edge of a connected graph G if and only if there exists a vertices V, U and V such that E belongs to every UV path in G. Proof. First you consider the cut edge E is equal to xy. Then G minus E has two components, say G1 and G2. Let U belongs to the vertex set of a first component G1 and V belongs to the vertex set of a second component G2. Then every UV path in G contains E. So we can clearly say that trivially every UV path contains the edge E. Conversely, suppose that there exists a vertices U and V satisfying the condition of the theorem, then there exists no UV path in G minus E. Because of by removing E from G, we cannot join U and V by any path. So that G minus E is disconnected, hence E is a cut edge of G. So next definition is connectivity. For a non-trivial connected graph G having a pair of non-adjacent vertices, the minimum k for which there exists a k vertex set is called the vertex connectivity, or simply a connectivity of G, and it is denoted by kappa of G, or simply kappa. So it's a Greek symbol. If G is trivial or disconnected, kappa of G is taken to be 0. Whereas if G contains Kn as a spanning subgraph, kappa of G is taken to be n minus 1. A set of vertices or edges of a connected graph G is said to disconnect G if its deletion results in a disconnected graph. So here connectivity means, for example, if you consider a graph with 5 vertices, someone removes 3 vertices, then then the resulting graph is disconnected. Someone removes 4 vertices, then the resulting graph is also disconnected. Someone removes 2 vertices, the resulting graph is also disconnected. So by removing 2, 3, 4 vertices, the graph should be disconnected. But the minimum number of vertices removed from a graph after removing the graph is disconnected is the number 2. So 4 is also we consider, and 3 is also we consider, but the minimum number is 2. Therefore the connectivity of a given graph G is 2. So by considering minimum vertices that satisfies the removal of that vertices, resulting a disconnected graph. So the kappa of G is 2. Next one is the edge connectivity. So it is the smallest k for which there exists a k edge cut. The minimum number of edges the removed after removing that minimum number of edges, the resulting graph is disconnected. That the minimum number is called the edge connectivity, and it is denoted by lambda of G. If lambda is the edge connectivity of a given connected graph G, there exists a set of lambda edges whose deletion results in a disconnected graph, and no subset of edges of G of size less than lambda has this property. Next definition: a graph G is R connected if the kappa of G is greater than or equal to R. Also G is R edge connected if lambda of G is greater than or equal to R. This one is a very important theorem. For any loopless connected graph G, kappa of G is less than or equal to lambda of G, which is less than or equal to delta of G. That means the connectivity of a given graph is also less than or equal to the edge connectivity of a given graph G, which is lambda of G, which is less than or equal to minimum degree of a given graph G. So these are all the inequality for the connectivity and the edge connectivity and the minimum degree of the given graph G. So this example explains the strict inequality for the above theorem. Kappa value is 1. So by removing the center vertex, the graph is disconnected. Therefore kappa value is 1. And here lambda is equal to 2. By removing the 2 vertices which is incident at the center vertex, then the graph is also disconnected. Here the minimum degree is 3. So delta is equal to 3. Therefore kappa is strictly less than lambda, which is strictly less than delta. Thank you.